So we're at the point where we're just about ready to start using the second order beam equation. And of course what we need is m of x. And m of x is the moment inside the beam. And so as you've read in your derivation, the curvature or the second derivative of v is equal to the moment over E times I, the cross-sectional moment of inertia. So for a determinate or indeterminate beam, we're going to need to approach them just slightly differently. And for a determinate beam, m of x is going to be a function of the applied external loads. And we're going to be able to solve for m of x by using statics, that we will have enough equations to be able to solve for all the unknowns. In an indeterminate beam, we have a problem in that we have too many external unknowns. So m of x will be a function of at least one of those external support forces. For m of x, we'll look at a couple of examples here very quickly. So we have a beam, a simple cantilevered beam. We've got a wall or a fixed support at the left end. We have a point load sitting out there at the end of the beam and a length L. So we define a coordinate system. And what we are going to do is use the blue saw. And the handle is the @blue saw at x. So that's what we're going to do, is cut this thing at a distance x. And after we cut it, we're going to use the free body diagram on the left, the one that does not contain the red arrows from the support force. So let's go ahead and look at what this free body diagram is going to look like. It's going to have a distance x to it. And what we've exposed at the cut are the three internal forces, m of x, p of x, and v of x. And this is valid everywhere from 0 to L. It's valid over the entire length of the beam. The function m of x is not going to change because we don't have any applied loads. So the quickest, most efficient way to solve for m of x is just to go ahead and spin a moment right at the cut. Just go ahead and spin it right there. And so if we do that, we have minus p times x minus m of x is equal to 0. And again, I've transformed. Here's my transformer. I'm going to transform from a picture into an equation. And moving along, then I can solve for m of x. And again, that is valid all the way from 0 to L. So I would go ahead and now be ready to use that in the second order beam equation. Let's look at another one. I've got another cantilever beam with an applied moment at the end. Right, it's purple. It's a parameterized external load, length L. Again, x is defined from the left. So to attack this thing, we are going to use the blue saw. And I'm going to cut it, and I'm going to use the free body diagram over on the right-hand side this time. Right? Again, avoiding the support forces. So there's our blue saw. Right? What do we end up with? We got a free body diagram down here where, again, we've exposed the internal forces at a distance x. And paying close attention here, this is probably the most important piece here, is we've cut this thing at a distance x. And if we had an overall length of L, then left over is going to be L minus x. So as long as we can dimension the other side of the free body diagram, we're going to be able to go ahead and use it. And the benefit of doing that is I don't have to solve for the support forces right there. So let's just spin a moment right at the cut again, and we would quickly then come up with m of x, which is a constant in this case, and it is going to be valid all the way from the left end of the beam to the right end of the beam. Let's look at another example. Now we have a cantilevered beam with a distributed load on it. So we'll be in that same ability here. We'll have the same opportunity, is that we can avoid solving for the reactions over at the wall. Not that they don't exist, but we can go ahead and cut and just use the other side of the beam. What we have to be able to do is dimension that free body diagram. So let's take a look at what picture emerges here. I'm going to cut that thing at a distance x, giving me left over, I'm going to have L minus x. So let's take a look at what that picture looks like down here. So there are my internal forces, right? The moment, the axial force, and the shear force. Got a dimension of L minus x. And what I'd like to do is solve for the internal moment. So I want to spin a moment right at the cut again. However, I have a need to do something first, and that would be to use a statically equivalent point load that represents the distributed load. This can only be done on this segment of the free body diagram. So I'm going to, just a moment, redraw this. And it's going to have a big dashed arrow that represents the statically equivalent representation of that distributed load. So that picture is going to look like the following. It's going to be located right at the centroid, which would be L minus x over 2. It's going to have a value of W, which is the magnitude, and it's a uniform magnitude, right? A constant magnitude, so I just have to multiply by the distance. So we get expressions getting a little more complicated here, but that is just a statically equivalent representation. And all I'm going to do now is spin a moment at the cut. Right, so what this statically equivalent point load does is now we don't have to integrate that distributed load, so it simplifies our math just a little bit. So if we go ahead and work through it, we would now have m of x, our expression for m of x at the cut right there. And now we'd be ready to go ahead and put that in the second order beam equation. Let's look at another one. We have a simply supported beam. We've got a roller at the right end. We've got a pin at the left end, has length L. On the beam is going to be a uniform distributed load. Right, this is a determinate beam here. Right, over here we've got 2 external supports. There we have 1 external support. So we have 3 external unknowns, and we would have 3 linearly independent equations of equilibrium. So this is going to be determinate. And so we're going to be able to solve for the internal moment, but we're going to need to solve for some of the support forces. And what we need to do is solve for support forces on at least one side of where we're going to cut our beam open. So let's go through the statics here. We're going to take that beam at the whole structure representation. We're going to put a statically equivalent point load from the distributed load that's going to be located at L over 2. And now I need to do some statics. Now I could solve for reactions at either side here. That's fine. I'm going to spin a moment over at the left end of the beam right there. That's going to give me an expression for F3. So that equation, right, is as follows. You can go ahead and solve that for F3. I get a positive number, and that positive number means that up back in the picture I had drawn, right, the arrow, the red arrow, is in, quote, the correct direction. So I would put or WL over 2 going up. Now at this point we are ready to cut this thing open, so I'm going to take out the blue saw again at a distance x. So I have defined a coordinate system, right, going left to right. So that is going to be right there. That is going to be at a distance x. And I'm going to use the side of the free body diagram that I solved for the reaction on. So I'm going to use the other side, sort of the right-hand side of the free body diagrams that result. And so that picture looks kind of nice. I've got the support force, the distributed load, right? A distance L minus x, right? I cut that thing at a distance x. If it has a total distance L, what's left over would be L minus x. And there are my possible internal forces. So just to solve for this, it's now just statics. And you can go ahead and chase that through a little bit. Let's go down, make sure you can see, the free body diagram and the equations that result. So that is our transformer. I'm going to transform this picture right there into an equation. And it's going to obey this transformation law right there. And so there's our expression for m of x. The one last one is going to be a triangular load. So we've got a beam simply supported, and it has a triangular load sitting on it. And so it's very similar to the uniform load, except just a little more complex because of the fact that the load is not constant. So we're going to have to again use statics to solve for some of the external forces. So let's go ahead and draw the whole structure free body diagram. We've got the left end a pin, we've got a roller at the right end. And this time what I'm going to end up doing is solving for all the internal forces at the left end, so I can sum forces in the x direction. That gives me that F1 is equal to 0, rather trivial. And I've also got the ability to go spin a moment over there at the right end. That's going to give me the expression to solve for F2. And so F2 has a value W naught L over 6. We also have used a statically equivalent point load for a centroid, the area of a triangle, 1/2 base times height. And it's going to be located 1/3 from the vertical edge. So we've got now a free body diagram that is solved enough, and the procedure is exactly the same. We're going to go ahead and blue saw that thing right at a distance x. I'm going to use the free body on the left side. So it is going to have a distance x to it. I'm going to also again now use a statically equivalent point load. So I would need the value right there of the top of the triangle, which is going to be W naught over L times x. And so the area underneath the triangle, 1/2, the base, which is length x, and the height, which is W naught over L times x. And there are my internal forces, and all we're going to do is spin a moment right at the cut. And so we end up with an expression for m of x. So what happens if the beam is indeterminate? Up to now it's always been determinate. So let's take this beam that has a wall fixed support at the left end. It has a roller over there at the right end. It happens to have a uniform distributed load on it. And let's just go ahead and draw the whole structure free body diagram. So the wall provides fixity from translation, which is modeled by F1 and F2, also from rotational movement. So I have a total of 3 unknowns at the left end. We have a roller support which provides 1 translational kinematic restraint. That gives me a total of 4 unknowns. And so if we can solve for F3 using statics, then we could go ahead and use the blue saw and cut it open. So that's what we need to do, is we need to have a free body diagram that has solved arrows, nothing but black arrows on one side before we go ahead and cut it open. So let's just do that. Let's just spin a moment at the left end right there. That might give us a way to solve for F3. So that equation then looks like, it's going to give us back up here, I'm going to have M10, I'm going to have the distributed load, and I'm going to have F3. So let's go ahead and look down here. There's M10, there's the distributed load, and this is going to be a statically equivalent representation of the distributed load. There's the lever arm, and then there would be F3. So solving for F3 is going to be a function of M10. I can't turn F3 black. It's only a function of another red arrow. So we will not be able to use statics to solve for the 4 red arrows, and we only have 3 linearly independent equations of equilibrium.